Since it's our last session together, I thought it would be a nice time to go and get an overview of the course. Now, there's no way we can talk about all the subtleties and all the ideas that we talked about. So I wanted to sort of pick on some of the bigger ideas, the important takeaways from the course. And we're going to go roughly in order. I don't want to say that one idea is more important than another idea, but certainly I would expect that if you tell anybody, yes, I took calculus, that these ideas that we talk about today are ones like, yeah, I remember hearing about those. So the first idea we're going to start with are limits and continuity. Limits are really important to calculus. In some sense, limits are that extra layer you add on to algebra to get to calculus. Now, what does the limit do for us? The problem that we often face is that there are some things that we want to know about, but we can't look at directly. So what we have to do is sort of look at it indirectly, and in particular ask the question, well, what should happen? So we have this notion of this limit. We say the limit as x approaches a if f of x is L, says that as x is getting close to a, f of x is getting close to L. So in other words, what should happen to the function at a? And not necessarily what does happen. They don't have to be the same. And indeed, continuity is a very nice function, and we like nice functions. It's where there's no surprises. What should happen to our function at a is what does happen to our function at a. Now, if you've seen limits, one of the things you may have seen is what's called the epsilon delta definitions. And that's just another way of saying, let me define closeness more precisely. So how do we handle limits? Well, to actually work with limits, there's a few things you do. Work with algebra, and you look for factoring or multiplying by conjugates. Look for trigonometry, identities, and in particular, sine squared plus cosine squared equals 1. That one gets an incredible amount of mileage. And of course, as we got to the end of the course, one of our favorites, le hôpital, oh, le hôpital, le croissant, le baguette, le hôpital. Le hôpital, it's a powerful tool that helps us figure out what happens when you get a 0 over 0 or infinity or infinity. Now, we couldn't use le hôpital at the beginning because we hadn't developed the machinery, but as we got closer to the end, the tools were in place, and yes, we were ready to go. So let's do an example that involves limits. Find a, b, c, so the following function is continuous at x equals 0. So I have this function, g of x. You'll notice it's a piecewise function. In other words, we're breaking up into three pieces. What happens above 0? What happens at 0? What happens below 0? Now, how do you work with piecewise functions? The answer is in pieces. Okay, so we need it to be continuous, and we have different behaviors from the two sides, which means that you say, all right, let's look at the behavior from the left, let's look at the behavior from the right, and they all have to agree with what happens at the point. Now, there's a couple of things to point out. Clearly, we have f of 0 equals b. So the question is, well, what should our function be? Now, look at these two from above and below. I would probably say that from the below might be more interesting to start with. So let's start here. So what happens to the limit as we go to 0 from below of g of x? Well, it's the limit as you go to 0 from below of 2 minus square root c minus x over x. And what you always do whenever you have a limit is you just plug it in. And you see what you get. Well, you get 2 minus the square root of c over 0. Now, we want our limit to exist because it has to be continuous, so the limit has to exist. That limit has a 0 downstairs, which means that we need the upstairs. This has to be something that has to also be 0, because if it's not 0 over 0, no chance. Well, so 2 minus square root of c equals 0, that tells us, lo and behold, c had better be equal to 4. So, now we know what c is. c is 4. All right, so we're a third of the way done. Well, it feels like we've hardly started. Of course, to be fair, we've hardly started. All right, well, let's go back. Now we know what c is. c is 4, so we get 0 over 0. Now we could do l'Hopital. We don't have to. Let's, flex our old conjugate muscles. So let's take this, and if you multiply top and bottom by 2 plus, remember that conjugation works by you flip the sign in the middle, so 2 plus square root of c minus x over 2 plus square root of c minus x. This is the old fact, multiplying by 1 doesn't change anything. Then what you end up with is upstairs you'll end up with, remember now c is 4, so let's go ahead and replace the c by 4. What you'll end up with upstairs is 4 minus x, all that divided by x times 2 plus, and whoops, that's a 4 there as well, square root of 4 minus x. Now 4 minus the 4, those cancel. Minus minus makes a plus x. And notice you have an x both upstairs and downstairs, which means that they cancel. In fact, the philosophy at the beginning, when we faced with this situation, is to say, if I'm getting 0 over 0, find a way to cancel the zeros. Same thing with infinity over infinity. Find a way to cancel the infinities. And if you do that, life is good. Now, that's a much easier expression to work with. And if I plug in 0, what do you get? Well, you get a number. Definitely upstairs you get a number. When you get a number, it's pretty much game over. So when you get downstairs, 2 plus square root of 4. Well, 2 plus 2 is 1/4. So that says that as we approach 0, and I should have kept putting the minus sign here, as we're approaching 0 from below, we know we need c equal 4, and it's going to approach 1/4. In order to be continuous, that has to match up with the function at 0, which is g of 0. So g of 0 is b. So now we know that b has to be 1/4. All right. So c is 4, b is 1/4. Nice. So we're now 2/3 the way through our problem. That leaves us with a. So let's look at this. So that says, let's look at the limit from above. X approaches 0 from above. Well, g of x, what will it be? The limit as x approaches 0 from above of sine of x plus e to the ax minus 1 over x. And I'm going to break this up. Sine of x over x plus e to the ax minus 1 over x. Just because I want to take a second and say, this is such an important limit. It shows up over and over and over again. That for the rest of your time in math, you should always remember the following. If you have sine of blah over blah, it doesn't really matter what the blah is, but what really matters is that the blah goes to 0, then this goes to 1. So that part is going to go to 1. Okay, so I can really say this is going to be 1 plus what the other part does. Now here, well, we really haven't had a chance to flex our l'Hopital. Oh, let's do our l'Hopital now. So notice that it's going to go to 0 over 0. So I can apply l'Hopital. So we get what? 1 plus limit as x goes to 0 from above. And I should say, if we're going to do l'Hopital, let's actually do it properly. And we say, got to check that it goes to 0 over 0, and got to mark that you're doing l'Hopital. Then take the root of the top, a e to the ax, root of the bottom, 1. Not a quotient rule. You're going to take the root of the top, root of the bottom, and that's an easy limit. That's going to get to a. So 1 plus a. But remember, that has to match with g of 0, which is b, which is 1/4. So, what is a? Well, that tells us then that a is 1/4, subtract the 1, so that's minus 3/4. So there's a, minus 3 over 4. So, now we have our answers. Minus 3 over 4, 1 over 4, 1. Now let's go ahead and put them all in a convenient box here at the bottom. So a equals negative 3 over 4, b equals 1 over 4, and c equals 4. That's it. Done. Good. Well, that's a nice idea. What's our next idea? Well, the next idea we talked about is we went into the notion of tangent lines. Now, why does this have anything to do with limits? Well, if you think about our basic picture, as we said, we're interested in rates of change. Now, for lines, it's very easy to find rates of change, because when we're talking about rates of change, we're saying, how does our input change with our output, or rather the other way around, how does output change with input? Change in y over change in x. Well, that should sound like something very familiar. That should be the slope. So the slope, if we have a flat thing, equals our rate. But the problem is, what if you don't have a flat thing? You have something which is a little bit unflat. Well, so here's where limits start coming into play. You said, well, zoom in. And if you zoom in, you said, oh, it's a little bit less flat. Well, okay, zoom in some more. And as you kept zooming in, it would become less and less curvy, and eventually, if you zoomed in enough, what you would get is you'd get something which looked like a flat line. So we said, okay, this notion of zoom in, that's a limiting idea, and that's where we get to this notion of our tangent line. So our tangent line is, what does our function look like when we zoom in? So that's the tangent line. Now the word tangent comes from touch. So it touches the function, but it also has information about the rate of change of the function, because that slope is measuring rate of change. So tangent line stores two pieces of information: the value of the function and the rate of change of the function, which we denote by this f prime of a, which we call the derivative of the function at a. And so it's useful and important to be able to go back and forth. Say, okay, if I know what the function is, I know what if I know what the function is at a and the derivative is at a, I can write down the tangent line equation. And if I have a tangent line, I can figure out what is the function at a, what's the derivative of the function at a. So I can jump back and forth between these two different ideas. Now, one other thing to remember about tangent lines, and this is one of the nice applications, is to remember that tangent lines are good local approximators. So that is to say that my function f of x is approximately f of a plus f prime of a times x minus a. In other words, the function looks like the tangent line. Now there's a caveat, which is this statement right here. You have to be near. The further out you move, the worse you get. You can imagine that, of course, this isn't so hard to see. You know, we come back here, it's like, all right, I have this tangent line, and close up, it's great. But far away, it's terrible. So that's a terrible approximation. So that's why we say near. Now you might want to say, well, how do you make better approximations? Stay tuned. Calculus 2 is going to be good. So here's an example. Y equals 3x minus 2 is tangent to y equals f of x at x equals 3. Y equals negative 4x plus 7 is tangent to y equals f of x at 5. And then it says find the tangent line to y equals f of 7 minus 2x, f of 4x minus 3 at x equals 2. Okay, well, how can we go about doing that? Well, let's first off take the information here. So let's start with this first line. That's storing information at 3. So remember, tangent line stores information at your point of tangency. So I can get the following: f of 3 and f prime of 3. So to find f of 3, plug it in. Whatever it says, that has to be the same because it has to touch. So if you plug in 3, 9 minus 2 equals 7. How about f prime of 3? Read off the slope, and that gives you your derivative, 3. Now if you come to the second one, similar process. We can get information about what's happening at 5, so both for the function and the derivative. So what do? We plug 5 in. We'll get negative 20 plus 7. Negative 20 plus 7, negative 13. And if we want information about the slope, just read off the slope. So at 5, the slope is negative 4. F prime of 5 is negative 4. Now, We say, all right, well, I need the tangent line to this function. So let's call g of x, this expression, f of 7 minus 2x, f of 4x minus 3. I'm after the following. I need to know what is g of 2 and what is g prime of 2. Because once I have that information, I can find my line. So, plug in 2. G of 2, well, that's f of 7 minus 4. That's f of 3. Plug in 2 here. 8 minus 3 is 5. So that's f of 3 times f of 5. So that's 7 times negative 13, which is negative 91. All right, done. Well, for g of 2, we need g prime of 2. So now we do g prime of x, and here's where we use rules about derivatives. We'll talk about rules about derivatives in just a moment. We need to have the product rule and a little bit of chain rule mixed in there as well. So the derivative of the first term, f prime, 7 minus 2x times negative 2 times f of 4x minus 3. Then leave the first term alone, times it by the derivative of the second term, f prime, 4x minus 3 times 4. So plug in 2. G prime of 2, well, that's going to be f prime of 3 times negative 2 times f of 5 plus f of 3 times f prime of 5 times 4. Well, we know these values. F prime of 3 is 3. So we have 3 times negative 2 times negative 13. These are big numbers. Well, that's all right. Numbers are numbers. F of 3 is 7. F prime of 5 is negative 4. And 4 is 4. Okay, so what do we get? Well, we get 3 times negative 2 is negative 6. Negative 6 times negative 13 is positive, and that's going to be a positive 78. Then we have 4 times 4 is 16. 16 times 7 is 112. And if you're worried, wait, do I really need to know that? Well, we'll give you numbers that are easier to work with. Now, 78 minus 112, can we do that? And yeah, we can do that. We can think about it this way. Now, how far apart are 78 and 112? Well, I can think of, to get from 78 to 100, I'd add 22. Then I'd add 12 more. So that says they're 34 apart, but because I'm subtracting the bigger one, I'll end up with a negative 34. Yes? Is that right? That sounds right to me. All right. Cool. So, negative 34. Well, that's our g prime of 2. So, what's our answer? Well, we'll put it right here. We've come into our formula. So, y equals negative 91. That's our f of 2, or rather g of 2. And then g prime of 2 minus 34 times x minus 2. And that's it. We don't have to simplify. That's it. We're done. Nice. I like tangent line problems. They're always fun. In fact, I like to say I'm really good at teaching calculus because I keep going off on tangents. Okay, so the next big ideas are rules for derivatives. So really you should think of the rules for derivatives as falling into two camps. So the first camp is there's a collection of functions for which we know the derivatives for explicitly. The biggest collection is of x to any power. Then you have log of x, e to the x, arctangent. Oh, arctangent. What a beautiful function. Then you got your sine, your cosine, your tangent, and your secant. So those are our building blocks, and I call those the building block rules. The other rules that you have are things for combining. So I take my building blocks and put them together. So one of the important rules, we almost never think about it, which says really derivatives are linear. I can break up over addition, I can pull out constants. You have the product rule, which says if I'm taking the derivative of a product of two things, I have to sort of be patient. Every piece gets its turn. So if I have f times g, first f gets its turn, and then g gets its turn, and then you add the results together. If you had f and g and h, you'd have three pieces. The chain rule. And the chain rule is super important, probably the most important rule. A function inside of another function. So how does that work? It says take the derivative of the outside, but leave the inside as it is, times by the derivative of the inside. Now the other two, we have logarithmic differentiation, and logarithmic differentiation is really useful if taking the log of your function would simplify your expression. So there are certain things that you encounter where it's like, things where it's like lots of products and maybe things in your denominator, or when you have powers where both the base and the exponent involve your variable. So this is when you use logarithmic differentiation. Essentially, when logarithmic properties are helpful. And logarithmic properties are helpful for pulling apart multiplication, for pulling apart division, and for bringing powers down. And then you have the derivative of the inverse. And 1 over f prime of f inverse of x. Now you might be thinking, you forgot a rule, the quotient rule. Well, you can remember the quotient rule, but if you don't remember the quotient rule, you can actually recover it from the rules here. Because you can think of a f over g as f times g to the power negative 1. So these are the really important rules. And if you count, there's 13 total rules here. That's not that many rules. And if you're thinking to yourself, okay, what can't I take the derivative of? And the answer is, there's nothing that you've seen this semester that if you use these rules, that you can't take the derivative of. So this is it. And in fact, I would say taking derivatives is actually kind of fun, because all you need are the rules and patience. And if you work through them patiently, very patiently, then you'll be fine. So here's another chance for us to do examples. Don't worry, not everything is going to have examples. But, the more examples you do, the better you get. So here, I'm looking for f of x. I want to take the derivative. All right, so I'm taking the derivative of this function. Now, what rules do we have? Well, we have a product rule. We have a chain rule. And then if you look at our building blocks, well, we have a log of x. We have a sine. We have x to a power. We have a secant x. What else do we have? We have e to the x. So we actually are doing a lot of rules here. In fact, this uses almost half the rules that we have. But you might not even think about it because you almost never really process just how many pieces we have working together. So what do we get? Well, when you're trying to figure out what the rule is, always think of it as sort of an onion. There's layers, building blocks. How do they put together? It's almost as if you have something made out of Legos and you want to say, how did I piece all of this together? Now in this case, the big block here is the product rule, and then you get into the pieces, and here you have a chain rule and a chain rule, and then you get into the individual pieces and so forth and so on. So, derivative of the first term, well, derivative of sine is cosine, leave the inside alone, times the derivative of the inside, derivative of log, that's 1 over x, and now you're done. Times it by the other function, e to the x squared plus secant of x. Plus, now you leave the first function alone, sine log absolute value of x, times the derivative of the second function. Well, if you ever have e to something, it's always the e to the something, and then you times that by the derivative of the something. Well, that's 2x, derivative of x squared, plus, here we're using the fact that derivatives are linear, secant tangent. And we're done. That's it. And once you practice the rules, life is good. So, we want life to be good. So that means, I guess we should practice our rules. Let's go to our next one. Okay, what's our next one? Well, our next one, g of t. Now this one, there's a clue on what you need to do. Not so much like a clue of what you should do, but something you have to do. And it's right here. That t to the power t. See, when you see t to the power t, that variable is both upstairs and downstairs. Well, that says you don't have a rule that really helps you with that. Plus, there's all this extra stuff floating around. So there's lots of things in your denominator. So what's going on? Well, this is a case where logs would be great. So this is a logarithmic differentiation problem. So the good news is we have the rule right there. So what do we have? Well, we have, give ourselves some space here, g prime of t is this original function, t to the t over e to the t arctangent of t, times the derivative of the log of t to the t over e to the t arctangent of t. Now you might notice that sometimes we put absolute values and sometimes we don't. You should always technically put an absolute value when you're using your logs. Most of the time, if you don't, it won't make any difference. Just be a little bit careful. Well, what is the key here? The key is that the power of logarithmic differentiation doesn't happen at the differentiation part. It happens at the logarithm part. So, in this case, if you apply the fact that you can bring powers down, that things in the numerator are added and things in the denominator are subtracted, this becomes t log t, that's our t to the t upstairs, subtract t, that's our e to the t downstairs, because it's log of e to the t, and log and e are inverses of each other, and minus log of arctangent t. All right, so we haven't taken any derivatives yet. Time for us to take a derivative. So we still have that t to the t, e to the t, arctangent t. In some sense, the hardest part about these problems is making sure you write everything out. T log t, use the product rule. So derivative of t is 1. So then times it by log t. Then plus t times the derivative of log t. Well, that's t times 1 over t, which is 1. And then what comes next? We're going to subtract t. Well, minus 1. Then minus the log of arctangent of t. So that would be minus 1 over arctangent t, because whenever you're taking the derivative of log, it's 1 over the inside, times the derivative of the inside, 1 over 1 plus t squared. Now in this case, we get a little bit of cancellation, which is kind of nice. So we can say that our final answer is t to the t over e to the t arctangent of t. And then we have times that by log of t minus 1 over arctangent of t times 1 plus t squared. And there's our answer. Cool. So for this one, and for many problems, it's really more about be patient. Work the problem. Work the problem. And then you'll be fine. Okay, so let's do the last one. H inverse at 0. Well, there's a clue. The inverse. Okay. So what does that tell us? Well, notice we want to evaluate it at theta equals 3. So what we're doing is we're going to really take 1 over h prime of h inverse of 3. So that's what we're after. Now, what do we do? Well, we got to figure out what is h inverse of 3. So we come up here and we say, okay, that doesn't mean we plug 3 into here. That says, what's the choice for theta? When we plug theta into it, we get 3 out. Now we could try to solve for it, but I think this is the case when we can probably guess. Well, what's a good guess? 1 seems pretty reasonable. 1 plus 1 plus 1 is in fact 3. So h inverse of 1 turns out, h inverse of 3 turns out to be 1. So that's 1 over h prime of 1. Now, what is h prime? Well, h prime of theta is 3 theta squared plus 1. You might be saying, hold on, am I allowed to use theta for something which doesn't involve trig? And the answer is, why not? It's a symbol. You can choose a symbol to do anything. So, yes, you're fine. So plug in 1, you're going to get 1 over 3 plus 1, which is 1 over 4. And there's our answer. And we're done. All right. Well, that's not so bad. Cool. So let's move on to our next big idea. And this is sort of a smaller big idea. So what's our next one? Let's talk about implicit differentiation. So implicit differentiation is when we have a relationship, and I'll just go ahead and say, here's an example where you have something where x and y are tied together. So they're not independent of each other. If you tell me something about x, that forces something to be true about y. However, we may not be able to solve for y. So for instance, there's really no way to solve for this in a clean way. So there still is a dependency. It's just not clear what exactly it is. Now here's the cool thing. It's actually not so bad to do an implicit differentiation problem. So how do we do it? Well, the answer is that whenever we see this, we sit there and we say, let me think about it. And the way you think about it is you say, oh, I know what I'm going to do. I'm going to think of y as being y to the x. So here we are. We're thinking. You can tell we have we're rubbing our chin. Yes. So that's the key. So even though you don't know what the relationship is and you can't find it, I can still think of it. And now we're going to take the derivative of both sides. When we talk about taking the derivative of both sides, we really mean with respect to our variable x. And the key is, whenever you see a y, you think, oh, y depends on x. And so that becomes, take the derivative of that and apply the chain rule. So let's go ahead and take the derivative of both sides with respect to x. So, see here, that doesn't look like there's a y, but because we're thinking of it as though there is, we say, oh, that's going to be the derivative of y with respect to x, which we write as the derivative of y with respect to x, or in shorthand, y prime. Here, e to the xy, well, e to anything is e to that something, then times the derivative. What rule? Well, we need a product rule, because there's two places x are showing up, the x and inside of the y. So this is going to become derivative of the first, which is 1, and times it by y, plus x times the derivative of y, which we'll write as y prime, derivative of y. So that's the derivative of the left-hand side equals derivative of the right-hand side. Derivative of cosine, negative sine. Derivative of 5x plus 5. All right, so we took the derivative of both sides. Now, what you'll be able to do, and you'll always be able to do this, and if you can't, you've made a mistake, is you'll be able to put everything with a y prime on one side and everything without a y prime on the other side. So here I'll leave the y primes on the left, negative sine of x plus 5, minus y e to the xy on the right. Now why are we doing this? Well, notice you can factor out the y prime. So you get 1 plus x e to the xy, and that's equal to our expression. And now solve. So we get that y prime is equal to minus sine x plus 5 minus y e to the xy. Divide that by 1 plus x e to the power xy. And that's y prime. So in other words, if you give me an x and y that satisfy the original relationship, I can say, well, here's what y prime is. Now you might say, well, what does that even mean? Well, what it means is that there's some curve here that exists. Now we just don't know what that curve is. So there's some sort of curve that's doing something. And we can say, okay, what the derivative is if you zoom in on the curve, that's telling you what that tangent line looks like nearby. So that's what that y prime is referring to at that point. Now, the next idea is related rates. Now, a lot of people confuse the two ideas of implicit differentiation and related rates because there's a subtlety here. Now, what's going on is you have these quantities which are related. So maybe we have x and y, or x and y and z, or any number, but there's some relationship. We say, well, you know, if the quantities are related, then the rates of changes are related. So we take the derivative of both sides. Now here's why people think that it's the same. We're taking derivatives of both sides. What's the difference? Well, in this case, we were taking derivative of both sides with respect to x, where x was one of our variables. And here, what we're doing is we're taking derivative of both sides with respect to some other variable t. So in other words, we have this thing, we oftentimes think of it as time. It doesn't have to be, but it's the most common one. And we're saying, well, how is everything changing as we're changing time? And that influences what goes on. So let's do an example. A fire truck has a ladder which is currently extended 50 feet and is extending its length by 8 feet per minute. Okay, so we have a fire truck, and what is it? Well, the ladder is designed to always maintain contact with the side of the building. So okay, so here we have our building, which, to help you see that it's a building, we'll label it building. All right. So then we have our fire truck. We'll put T for truck, and there's this ladder here that's been extended 50 feet. All right, what else do we know? So the ladder truck is currently 30 feet from the building. So here's 30 feet, and is moving away at 5 feet per minute. Determine if the ladder is moving up or down the side of the building, and also the speed it is moving. Now, one of the things that's happening is we really have a nice triangle. Let's assume this is one of these reasonable buildings, not one of these modern art buildings. So we have this triangle here, and it's not just any triangle, it's the right kind of triangle. And so we have a relationship. Now, a lot of related rates problems are built off the Pythagorean theorem or similar triangles. There's a lot of geometry that goes into them. It doesn't have to be. There are other things that can happen. Sometimes you'll get an explicit relationship given to you. But okay, so we have this relationship. And we have these three sides. So let's label these three sides. Let's call this X, we'll call this Y, we'll call this Z. Now, what do we know? We know that they're all changing. So the ladder is moving up or down. That says Y is going up or down. X, it's moving away. Z is extending. So let's label what we actually know. So we know that currently we have the following pieces of information. We're told that the truck is 30 feet away and that it's moving away at a rate of 5 feet per minute. Okay, so that says dx dt is 5. We also know that the ladder is currently extended to 50 feet and that it's growing dz dt at 8 feet per minute, and it's growing, getting longer, so that's 8. So that's what the problem gave us, but there's one other thing we can actually figure out, which is what y is. So we know what y currently is because we have this right triangle. In fact, this isn't just any right triangle. 30 and 50, well, it's like the 3 and 5, just scaled up by 10, which means that the other side will be 40. Now you might think, that triangle gets used a lot. Why do we keep using that triangle over and over again? Well, the answer is we want to have problems that we can do without a calculator, so 3, 4, 5 works pretty well. Not because you're going to encounter a lot of triangles that have exactly 3, 4, 5 in the future. Right now, we're building up our intuition. Okay, so that's currently what we know. What do we want? Well, what we really want is to get some notion of what is dy dt. And of course, I should have said there's one other thing that we currently know, which is that x squared plus y squared equals z squared. So this is our information that we currently know. That's what we want to find. So how do we do it? Well, we start with our relationship, x squared plus y squared plus z squared. And then we take, let's try that again, x squared plus y squared equals z squared. There we go. And then we take the derivative of both sides with respect to t. So we'll get 2x dx dt plus 2y dy dt is equal to 2z dz dt. And if you're wondering what just happened there, what we did is we did something similar to what we had over here, is we said, let's think about everything that's varying as being some function of t which we don't know. And so I can think of it really as x of t, y of t, and z of t. We can cancel off a 2 right away. And now we say, well, hey, there are 6 pieces. We know 5 of them, and we want the last one. So we're going to put in all the pieces that we know and clean it up, and hopefully we'll get the part that we don't know, and that will tell us the answer. So we have x is 30, dx dt is 5. Y is 40, dy dt is dy dt, because we don't know it. We'll find that out soon. Z is 50, and dz dt is 8. So, well, what is that? Well, that's 400, subtract 150. So you get 40 dy dt is equal to 400 subtract 150 is 250, or we get dy dt is equal to 25 over 4. So that's the answer. Dy dt is 25 over 4. Now, the question is, well, what's happening? Is it moving up or down? Well, that's a question of the sign. So here, it's a positive sign. That means that the y is increasing. If y is increasing, that means it's going to be moving up. So, moving up. That's the first piece. And the speed, well, that's the size of the number. At 25 over 4, and if we want to know the units, well, it's going to be the same units as what we have for time and distances, because everything is measured in feet for distances and minutes for time. And so there's our answer. Moving up at 25/4 feet per minute. Good, good. All right, well, now let's move on to our next idea. So, what's our next idea? Our next idea are critical points. And these are very critical to understanding what happens. Now, what is a critical point? Well, essentially these are the important points of the function. The points that we look at and say, something interesting is happening here. So these are places where the derivative is 0, the derivative is undefined, or you're at a boundary. Now, where does the derivative 0 happen? Well, that basically just says that the tangent line is horizontal. So it could happen at several places, like if you come up and come back down, or maybe come down and come back up. It could even happen that you come up, level off, and then keep going up. There's lots of things that could happen, but that's the place where the derivative is 0. How about derivative being undefined? Well, that could be, for example, if you have a kink like absolute value, or you might have something where you have a vertical tangent line, like cube root of x is an example. And the boundary, that is at the end. So we might have a function which is only defined between a and b, and so a and b would be critical points. Now the reason we care about the critical points is that the max and mins have to be at a critical point. Be careful, that does not say that if you're a critical point you're a max or a min. So for example, this curve, which has the same shape as x cubed, that would have a critical point but not be a max or min. So how do you figure that out, whether it's a max or min? The answer is you look at the first or second derivative. So let's first do this by example. Find and classify the critical points of f of x, which is x to the 15th e to the minus 3x. Well, there's no boundary given, so that says look at the derivative. So we take our derivative. F prime of x, well, product rule, derivative of x to the 15th, 15x to 14, e to the minus 3x, plus x to the 15th, then times it by the derivative of e to the minus 3x, which is negative 3 e to the minus 3x. Now, this looks a little bit daunting, but remember, you have the ability to rewrite things. So in our case, what we can do is we can pull stuff out. So if we pull out all our common terms, well, what's common? 3 is common, because 3 does divide 15, and 3 certainly divides 3. X to the 14th, and e to the minus 3x. So if we pull that out, and let's actually pull out a negative 3 while we're at it. Negative 3, x to the 14, e to the minus 3x, times, well, what's left? From our last term, we pulled out everything except a single x. So there's x. From the first term, we pulled out everything but a 5. But because this was positive, we pulled out a negative, it becomes minus 5. Now we say, okay, this function, never undefined, it's a good function. It's a nice function, the kind of function you want to take home to meet your family. Well, when is it 0? Well, e to the negative 3x, never 0. Good fact about the exponential function. X to the 14th, well, that's 0 at x equals 0. And x minus 5 is 0 at x equals 5. So we get critical points are going to happen at x equals 0 and x equals 5. Okay, so those are places where we might have a max or a min. So how do we determine it? Well, if we're going to use the first derivative test says let's look at the behavior. Now, what does the first derivative tell us? It tells us increasing or decreasing. In other words, is your function going uphill or is it going downhill? So we can use this information and we can do a little plot here. We'll mark our points, 0 and 5. And now we say, well, let's look at the sign. And so we pick a number. Let's pick something like 10. 10 minus 5 is positive. E, again, it's always positive. 10 to the 14th is positive. And then negative, we'll make it a negative. So that says that f prime is negative. If I pick something between 0 and 5, well, 1, negative, positive, positive, negative. Put that all together, you get that, what happens is you get a positive, right? Because you get two negatives combined together. Plug in a negative 1, negative, positive, because it's an even power, and positive, negative again. So it's still positive. So what happens? Well, it says you go up, and then you go up. So at 0, it has this behavior, going up and going up. Therefore, 0 is not a max or a min. Okay, what about 5? Well, at 5 we go up, then we go down. So if you're going up, then you go down, well, that says that 5 is a max. In fact, you can say it's a local max, but you can even be more assertive and say, not only is it a local max, it's a global max. Because everywhere before 5 you're going up, and everywhere after 5 you're going down, and therefore 5 is the largest your function can ever get. This is kind of the nice thing about calculus, is you can answer questions about what's the largest value, what's the smallest value. All right, so that's the classification. So again, first derivative tells us something about function is increasing or decreasing. What is the second derivative? Well, the second derivative tells us about concavity. Now, I will say that between the two tests, we should probably stick with the first derivative if it's a viable option. The second derivative has issues. First off, the second derivative might be hard to compute. So this would end up giving us several different terms, and end up with 3 terms at the end. But it would take a long time to compute. The other thing is that the second derivative is potentially inconclusive. In fact, if you were to apply the second derivative test at this function at x equals 0, it turns out the second derivative is 0 because we have that huge power of x. And that's going to force the second derivative to be 0. Now, what is concavity telling us? Well, concavity tells us how the curve is bending off the tangent line. So if this is my tangent line, so here's my tangent line. If I'm at my point here, concave up says I'm over here. So this is the upside. Concave down says I'm over here. This is the downside. All right? So that's what concavity is telling us. How does the curve bend off the tangent line? And in particular, we have a couple of things. The way I like to think about it is if your second derivative is positive, your concave up, you have a shape that looks like a smile. And in particular, if you're at a place where you have a flat tangent line, that says you're at a min. If your second derivative is negative, that says your derivative looks like a frown. And so if you're at a critical point, second derivative is negative, that means your curve is going down, you're at a max. And if your second derivative is 0, you just have no idea what's going on. Not enough information to make a decision. So that's the first and second derivative. So that leads us to our next idea, which is optimization. So why do these ideas lead together? Well, critical points oftentimes ask the question, what's the largest or smallest point? You're trying to find max and mins. So when you're talking about optimization, you're really talking about saying, I want to find the largest or smallest of some situation. And usually when you're doing an optimization problem, you're having to do a trade-off. Your trade-off is between sort of two situations. And so you have to figure out, okay, how do I balance the demands of these two conflicting situations? Because if you don't have to make a trade-off, then it just says, okay, do as much as you can. So let's do an example. A silo will be built consisting of a cylinder with a hemisphere on top, also known as a silo shape. Now you have a budget of $180 for the materials. The sides, they cost 1 over pi dollars per square foot, and the hemisphere costs 4 over pi dollars per square foot. What are the dimensions that will maximize the volume? See, there's a constraint. We don't have infinite dollars, so we can't build an infinitely big silo. So what does the silo look like? Well, it looks a lot like the following. You have a cylinder, if I can draw a cylinder. So you have a cylinder, and then on top of that, you have a hemisphere. So that's what a silo looks like. So there's two things that we can play with. One is we can play with the height of the cylinder, and the other thing we can play with is we can play with the radius. So I'll mark it up here. That's our R. So we want to maximize our volume. So we say, okay, well, our volume consists of two pieces. It's the volume of the cylinder, which you find by taking the area of a circle times the height, plus half the volume of the sphere. Now, it's good to know the volumes of various things. The volume of a sphere, turns out, is 4/3 pi r cubed. We would probably give that to you on a test, though. Don't spend your time worrying about whether or not we're going to give you 4/3 pi r cubed. Or just for fun, just memorize it. Pull it out at a party and be like, whoa, that person knows that the volume of a sphere is 4/3 pi r cubed. They sound cool. I want to go hang out with them. Yep, that's what people do. They like to hang out with mathematicians. All right, so there's what we're trying to optimize. Now notice, what do we have? Well, we have constraints of money. We could make h very large, but because if we make h large, we have to spend a lot of money on the sides. That would mean we have to make r very small. Or we could make r very large, but then the h would be very small. So there's this trade-off going on, and the optimization says, where's the right place that everything balances out? So let's do the other part, which is the money. Okay, so we have a budget for materials. So we say, look, how much area is there? Now, what do we have? We have $180, and that has to equal the money we spend on the materials. So think about the cylinder. Now, what you can do is, if you want to think about the cylinder, is grab a pair of scissors and cut. And if you cut the side of the cylinder and lay it flat, you'll get a rectangle. The rectangle has area where the height is h, and the length is the radius laid flat. Well, the diameter is 2 pi r. So the area from the cylinder is 2 pi rh, that rectangle when we lay it flat, times 1 over pi. Now, how about the hemisphere? Well, it's half a sphere. You might say, okay, now what's the surface area for a sphere? We've actually mentioned it before this semester, but I'll go ahead and just tell you. 4 pi r squared. And again, this is something we would give you. Now you'll notice that's the area. What's the cost? The hemisphere is more expensive, 4 over pi. All right, a little bit pricey, but that's okay. So what do we end up with? Well, we can certainly cancel off a bunch of pi's. That's good for us. And what else can you do? Well, okay, 2 can go into 4, makes it 2. And then I can divide everything by 2. So we can conclude that 90, if I divide that by 2, divide this term by 2, that 2 goes away, is equal to r times h plus 4r squared. All right. Now, what happens next? Well, our ultimate goal is we want to solve for volume. And in order to use our tools, we have to get down to one variable. Right now we have two. We have R and H. But this gives us a constraint on R and H. So if I solve, I can say, okay, well, notice there's only a single H up here. So I can solve. Actually, I can do something a little bit sneaky here. I can just say that R times H is 90 minus 4R squared. Why do I say that's a little bit sneaky? Come back here. Notice that this is equal to pi times R times H plus 2/3 pi R cubed. Therefore, we can write that volume as just a function of a single variable R is pi times R times 90 minus 4R squared plus 2/3 pi R cubed. Or, if you multiply this through, you get 90 pi R, then you get minus 4 pi R cubed plus 2/3 pi R cubed. Let's go ahead and take our derivative, v prime of R. So we're trying to find a max-min. Max-mins have to occur at critical points. So take the derivative. Here we'll get 90 pi. That's our first term. All right, minus 12 pi R squared. And here, 3 comes down, plus 2 pi R squared, which is 90 pi minus 10 pi R squared. Now this derivative is never zero. Sorry, it's never undefined. When is it zero? Well, we set this equal to 0. And we say, okay, well, what would have to happen? I'd move the 10 pi R squared across, divide by 10 pi, and that would tell us that R squared had better be equal to 9, so R had better be equal to 3. All right, so there's what R should be. We've now solved for R. Well, how do we get H? Now, you might say, wait a second, how do you know that's your answer? Well, okay, that's a good question. You would go through and you would do things like, for example, test what happens on either side. If I plug in R equals 0 into our derivative, we get 90 pi. Okay, that's positive. If I plug in R equals 1,000,000, well, it doesn't make sense, but if you plug it in, so you get a negative. So, positive, negative, max. All right, R equals 3. What is H? Well, so come back up to your relationship. So plug it in. 3 times H is equal to 90 minus 4 times 9, 3 squared. Well, that's really what? 90 minus 36, which is 54. Yes? It is. Yeah, 54. 3 times H equals 54. Well, divide by 3. H becomes 54 over 3, also known as 18. So, we get a radius should be 3 feet, and our height should be 18 feet, which, as silos go, is kind of a really little tiny silo. But, you know, as math problems go, it's fun. Okay, so we can do optimization problems. So the key is get down to whatever you're trying to optimize as a function of one variable. And so the hardest part about optimization problems is almost always the how do you get to one variable? And that is look for relationships, figure out what is it you're trying to maximize or minimize, and write stuff down. You can do this. You can do this. I believe in you. You're good. You're good. All right. So that's sort of the end of the derivative phase. Now we go into the next, which says, look, I've had enough. Enough of these derivatives. On to antiderivatives. Okay, what is an antiderivative? So an antiderivative is essentially a function whose derivative gives you what you want. So I have a function little f. I'm looking for a function big F, where if I take the derivative of big F, I get little f out. Now the nice thing is that antiderivatives are known to exist. If you have a continuous function, it must have an antiderivative. Bad news, it's really hard to find them sometimes. And we'll get into that in just a second here. They're not unique, but if you say up to a constant, then they are unique and life is good. So how do you actually go about doing it? Well, the good news is because antiderivatives are based off of derivatives, you start with saying, I know some basic derivatives, and go back to there, and you get some basic antiderivatives. So x to a power 1 over x. Remember, x to the power, there's that special case of 1 over x. That behaves differently, log x. E to the x, 1 over 1 plus x squared. Ah, wow, arctangent, crazy, and beautiful. Cosine, sine, secant squared, secant tangent. So we have a whole bunch of things that we can take antiderivatives of. Now, how do you find them? Well, there's actually only a couple things you can do. So it's important to understand that finding antiderivatives is a little bit different from finding derivatives. For finding derivatives, we had those 13 rules we had earlier, and if you have those rules, you're always going to be able to find the answer. It's just a matter of how patient are you. And if you're patient enough, life is good, and you're done. But with antiderivatives, it's tough. So here's what you do. You say, is this one of the antiderivatives I should know? In other words, is it on my list? And there's only 8 things here, so you should know all 8 of those. And really, you should toss on 2 more when you hit Calc 2, integral of tangent, integral of secant. But for now, we're okay with this list. If it's not one of those, basically your only hope is to say, let me try to make it look like one of those. So how do we do that? Well, use algebra or trigonometry to rewrite. You can use linearity to separate. So when we're talking about linearity, like f plus g, and be really careful, because there are a lot of people that make mistake. Addition in your numerator, awesome. That's your friend. Work with it. Addition in the denominator, a challenge to overcome. And so don't just be like, aha, let me come up with new algebra because it makes it easy to do. No, no, no. No new algebra. Let's not be creative. This is not what our goal is. Our goal is not to be creative. Our goal is to get the right answer. The biggest tool you have, and this is the one that you should really work with over and over, is substitution. So substitution is based off of the chain rule. So it says, if I have the integral of f of g of x times g prime of x dx, I can simplify this to thinking of this as the integral of f of some variable I'm calling u du, where what's happening is u is a stand-in to represent our g of x, and our du is a stand-in for this term g prime of x dx. What you're doing here is you're simplifying your expression, and that's what you want. You always want to try to say, let me make things as simple as possible. Because if I make things as simple as possible, then there's a chance, a small hope that we can make it work. And that's what we're always hoping for, is that chance. So we're going to do some antiderivatives as we work through these other problems. I'm not going to do a specific example with this idea. So related to antiderivatives, there's this notion of differential equations. And this is a really important topic. It's so important that there's whole courses set aside, not just one course, multiple courses set aside to solving differential equations. And what that says is you have something where I'm trying to relate a derivative with the value of the function. And this happens a lot more than you might think. This happens frequently in physics. So we say, okay, I have these expressions. What's my original function? And it's tough. It's tough. Finding antiderivatives is tough. And I'll say that there are antiderivatives out there that no one can do. There's even an antiderivative that's worth $1 million if you can solve it. Well, good luck. It's tough. So, anyways, but what do we have? Well, for some differential equations, there's a nice way to solve, and these are called separable differential equations. And here's the process. 3 steps. Separate, integrate, uncomplicate. So you just remember, 8, 8, 8. Separate, integrate, uncomplicate. All right, so let's do an example. Given that y times y prime minus x y to the fourth is x, and that y of 0 is 1, find the function y of x. So let's start with the first case, which is to separate. So first off, the key here is to think about y prime. I'm going to think of that as really dy over dx. And when we're talking about separating, what we want to get to is the point where I put all the y's on one side and all the x's on the other side. So first off, I'm going to try to isolate this dy dx. So I'll have y dy dx is equal to x plus xy to the fourth, and now here's the nice thing. Pull out the x. 1 plus y to the fourth. Now when we're talking about separation, that says I want everything with a y on one side, everything with an x on the other side. So we're going to do a little bit of a cheat, and I know that I've said don't do this, but please bear with me and say, okay, he can do it, so can I. And here's the cheat. You see this dy dx? dy dx represents a single thing. It is not a dy over a dx. But let's pretend it were. So now I'm going to think of dy as somehow being separate from dx. And if I do that, I'm going to say, okay, I'm going to move this dx over to there, and this 1 plus y to the fourth over to there. And what do you get? You get y over 1 plus y to the fourth dy is equal to x dx. And this is what we mean by separate. You have all the y variables on one side, all the x variables on the other side. Life is good. Okay, so now let's integrate both sides. So this is step 2, integrate. So since we're in step 2, I'll go ahead and change colors here. So if I'm integrating, well, to integrate x, it's probably easier to integrate 2x. So I'm going to go ahead and put a 2 here, and I can do that if I put a 2 over here. That's just for simplifying. All right, now one of these two sides is going to be easy. This side, integral of 2x dx, well, that's x squared. And then we tack on a constant, because we always have a plus c, remember? Derivatives are unique, antiderivatives are unique up to plus c. Now on this side, a little bit less clear, because 2y over 1 plus y to the fourth is not on our list. So we start thinking to ourselves, okay, where can we get this? How can we figure this out? One thing we're not going to do is we're not going to break this up as 2y over 1 plus 2y over y to the fourth, because that is not how algebra works. So algebra, you have to follow the rules. You can't just make up new rules. But there's a couple of clues. Now, when you're thinking about substitution, you always think about what substitution to make. There's the g of x. Look for the function on the inside. That can sometimes be hard. But the other thing is say, okay, is there something that's a nice derivative? Now you look at it and say, I recognize that as being the derivative of something else. Now in this case, we might say, 2y. That would be the derivative of y squared. Okay, so that could be our substitution. So that's a clue. Try u equals y squared, du equals 2y dy, because we have that 2y dy just right. Now the other thing is to think about, okay, what do I look like? Well, because of that plus downstairs, I should think, hey, I kind of look like this 1 over 1 plus something squared. Well, what is y to the fourth? It's y squared squared. Say, oh, make a substitution for y squared. And then that's the other place to look for it. So being really familiar with these basic 8 can be a very helpful tool in figuring out your substitutions. So if you make that substitution, what you end up with is du over 1 plus u squared, which becomes what? Well, it's arctangent of u plus c. Okay, so that's the integral there. So that says that the integral here, well, is arctangent. Got to replace u by what you started with, which is y squared. Now, you might say, do I need a plus c? And the answer is no, not here. The reason you don't need a plus c there is you already have a plus c there. See, these are going to be both constants. You might as well merge them together into a single constant. So, now we have our integrate. So that leads us to our next stage, which is to uncomplicate. So, how do we uncomplicate? Well, we're going to use this information. This information says, when I plug 0 in for x, y is 1. So, that tells me if I plug in y equals 1, I'm going to go ahead and just plug in right here, and x equals 0, then this has to be true. And if you look at that and say, hey, I know arctangent of 1, that's pi over 4, so that tells us that what c is. So now I know what c is. So arctangent of y squared is equal to x squared plus pi over 4. Now I really want to find the function y. So that says I've got to get y by itself. So I've got to get rid of the arctangent. Well, that's not so bad, because I can do the inverse of arctangent, also called tangent, to both sides. So y is tangent of x squared plus pi over 4. I say, well, look, I really want to get just y. So I'll take the square root. Now, do I need the plus square root or do I need the minus square root? And why is it the plus? Well, I need the plus because I need it to be a positive value at 1. So y is the square root of tangent of x squared plus pi over 4. Exactly what we would have thought, right? Probably not. We probably wouldn't have thought, oh, that's what the function is that satisfies that relationship. But we don't have to make wild guesses that will probably be wrong, because we have processes. And if we follow the process will work, which is good. All right. On to the next idea. Well, we've talked about antiderivatives. There's another idea which is related to it, which are called definite integrals. In fact, it's very similar. We use the same notation. So what's the definite integral? Well, notice that we have the same symbol here. So we use the same symbol. That's not a coincidence. We'll see why in a second. And what a definite integral is looking for is it's saying, what's the total? Now, a lot of people think, oh, definite integrals mean area. That is one way to interpret a definite integral, and you should keep that in mind of using the geometry, like for circles and rectangles and triangles. But that's not the only thing that a definite integral is for. A definite integral is about finding totals of things. In particular, the total under the function f of x from a to b. Now, how should you be thinking of this? Well, this symbol here, the way you should think of it is like you took the letter s and you stretched it out. And what is an s? Well, s for sum. So integration is about adding up lots of little pieces. And our little pieces are what happens when you multiply f of x, the value of the function at x, times a very small change in x. Oftentimes when we think about this geometrically, we think about these as rectangles. Small, skinny rectangles being added together. Now, some important things that you should keep in mind when working with definite integrals. Look for symmetry. In particular, if you have a really crazy looking function that you're asked to integrate, and they're going from like -4 to +4, or -8 to +8, see if you have an odd function. Because symmetry can help you cancel stuff out. Remember, what do odd functions do? Well, odd functions have this sort of behavior wherein you say, oh, if I'm going from -b to +b, these pieces will cancel each other out. So that's why we say symmetry is useful to keep in mind. Some other things, if I go from a to a of f of x dx, I can get 0. If I do integral a to b of f of x dx, I get negative the integral from b to a of f of x dx, which means that really when we talk about definite integrals, there's an orientation. Orientation matters. And so pay attention to that. That can help a lot. Integral from a to b of f of x dx plus integral b to c of f of x dx is the integral from a to c of f of x dx. So notice the key here is that these things match. So if they match, you can chain them together and thus make a bigger thing. Now, how do you do definite integrals? We're going to talk a little bit about a technique in just a few seconds. But one thing you can do is you can always estimate these. So even if you can't find a nice expression, you can always get an estimation by breaking things up into small parts. These are called Riemann sums. And if you, let's say, well, can you do better? Yes. And we'll talk about that in Calc 2. Oh my goodness. We have so much to look forward to in Calc 2. It's going to be a blast. Okay. So, what's the next idea? The next idea is the fundamental theorems. So, this is the idea that ties together the two things we've talked about. So, on one hand, you have the derivatives, which say, how are things changing? On the other hand, you say, you have integration. What's the total? And now you say, hey, these two things come together. So there are two variations. If I look at the integral from a to x of f of t dt, and I take the derivative of that, that's f of x. So this integral from a to x, that's a accumulation function. Another thing, and this is the variation that gets used more often, says, hey, if I have an antiderivative of little f, and I want to know what happens from a to b of the integral of little f of x dx, that's capital F of b minus capital F of a. In other words, I just have to evaluate the antiderivatives at the endpoints. And this is true as long as your function little f is sufficiently nice. Continuous is more than enough. So these are the fundamental theorems. It basically says, hey, if I want to do a definite integral, I just have to worry about finding an antiderivative. And that's how we oftentimes do our definite integrals, but it's not the only thing. As we said, we have symmetry, geometry, all sorts of other tools available to us. All right. Well, let's find the derivative of the integral x to x squared e to the t sine of t squared dt. Now what's going on? Well, it looks an awful lot like we're taking a derivative of an integral, because we're taking a derivative of an integral. So that's why it looks a lot like that. Now, suppose that was a constant. It's not, but let's just for the second suppose it were. What could we do? Well, the answer is that it's almost like this, except we replace x up here by x squared. So it's like we put the x squared function inside of here. Almost like a chain rule, because it's a chain rule. Now you say, well, okay, how do you handle that x? And the answer is, well, you do something similar where you break things up into pieces. And you flip, and it works out. In fact, here's the general rule. I want to take the derivative of the integral, say, g of x to h of x of f of t dt. Well, chain rule, you take f, plug the inside in, times it by the derivative of the inside. Now, why do I say the derivative? Well, that's the fundamental theorem of calculus up here. Plug the inside in. Then, for the bottom part, subtract. So oftentimes we think of the top minus the bottom. That's our orientation. So subtract f of g of x times the derivative, g prime of x. So this problem, you can actually just write down the answer. So it says, okay, plug in x squared into your expression. So e to the x squared sine of x squared squared. So when I say plug x squared in, everywhere I see a t, I put an x squared. Times that by the derivative of x squared, which is 2x. Subtract. Now everywhere where you see a t, put x. E to the x sine of x squared times the derivative of x, which is 1. And that's it. We're done. That's our answer. And life is good. Now, that brings us up to our next idea. All right. There's so many ideas, but don't worry, we're near the end. Idea number 12, mean value theorems. And these are nice to just sort of keep in mind. We don't use these very often directly, but they are important for the theory. So the mean value theorem says what? So suppose I have an interval from a to b, and it says if f of x is nice, well, nice being usually differentiable or continuous depending on context, then somewhere in the middle, for some c between a and b, you have f prime of c is 1 over b minus a, f of b minus f of a. Now that's the differentiation. How do we understand that? Well, if you look at this part, 1 over b minus a, f of b minus f of a, this is your average rate of change. In other words, how much has a function changed in between the endpoints? The f prime of c, this is your instantaneous rate of change. In other words, what's happening exactly at c. So the analogous thing to think about is the following. If I know my average speed in driving, say, to a nearby city is 65 miles per hour, then at some point on my trip, I had to be going exactly 65. So that's sort of the idea. There's also a mean value theorem for integration, and that says, look at the following. 1 over b minus a, integral a to b of f of x dx. Now this is what we call the average value of the function. And we say, if I look between a and b, then somewhere I'm going to have the exactly average value of the function. Okay, now if you look at these two things, you might start to say, oh, they kind of look similar. Here you have 1 over b minus a in both of them, for example. And if you start thinking about, if I think of saying capital F of b minus capital F of a, well, that would be that integral. If I think of the derivative of capital F, that'd be just f. So in fact, they really are expressing a similar concept, just in a slightly different way. So let's do an example to see that they are similar, but they aren't the same. They're not the same. Suppose our function is x squared, and we're going in the interval a less than or equal to x less than or equal to b, and a and b are both positive numbers. So determine the c which satisfies each variation of the mean value theorem. So the nice thing about our function f of x is it's really easy to compute things. So the derivative of f prime, so this is our differentiation. What do we get? Well, we get f prime of x is 2x, so f prime of c would be 2c would be equal to 1 over b minus a times b squared minus a squared. Well, b squared minus a squared, that would be the same as b minus a times b plus a. You get cancellation, and therefore your c would be b plus a over 2. So that's your c for the mean value theorem when it comes to differentiation. Now, integration, will we get the same c? Well, let's find out. So for integration, which I don't know if there's a good way to abbreviate that, well, what do we get? F of c, so that's c squared, is 1 over b minus a, integral from a to b of x squared dx. So that's 1 over b minus a. The integral of x squared, we know how to do that. That's 1/3 x cubed. Evaluate that from a to b. So that's 1 over b minus a times 1/3 times b cubed minus a cubed. Because I plug in x equals b, I subtract x equals a. Now b cubed minus a cubed, it turns out that's something which you can factor. It's just like b squared minus a squared factors. It factors as b minus a times b squared plus ab plus b squared. So the b minus a's cancel. And now we know that everything has to be positive, and the reason we know it has to be positive is because we are told a and b are positive. So when I solve for c, I better end up with a positive, because c has to be between a and b. That's what it says up at the top. So what do we get? Is that c has to be the square root of b squared plus ab. Oh, why did I have b squared there twice? That should be an a squared there. Plus a squared all over 3. And that's it. And you'll notice those are not the same. But that's okay, because these are slightly different ideas. One is about how is your function changing, one is about what's the average of your function. So it's okay that they're different. Which brings us to our last idea, which is area. So in some sense, when you're computing your average for your function, you really are talking about the average area, if you think of this integral as being area, but really you should think of it as being area with quote marks, by which we mean there's a signed area. Area could be positive or negative. So here, when we're talking about area, we're really talking about area without any quote marks. So we can talk about a couple of different situations. I can talk about area below a curve. So here's A and B, and I can say, okay, what's that area? And I can also talk about area between two curves. So when I'm talking about that, I have two curves, and it could be something like that, and I'm saying, okay, I want to find that area. So how do we find it? Well, the basic way we do it is we say if I'm after area, I can think about this as integrating height dx. And I know I didn't put bounds here, but I really should have bounds, because these are definite integrals. We're looking for numbers. A, B, R, C, D. And now, why do we think of it as height dx? So whenever you're thinking about integration, you always think about breaking things into little pieces. So we can think about it as like, well, I'm going to break things up into little teeny tiny rectangles. And I'll say, all right, what's the area of just that little piece? Well, the area would be the height of that little rectangle times the width of that little rectangle. So I'm thinking of the width, that small change in x, that's our dx. So that's the area of one little rectangle, add them all up, and that's the total. So when you get into applications of integration, spoiler alert, more stuff you do in calculus too, you're going to start saying, okay, I'm really thinking about breaking things into small parts and adding up the small parts together, and that gives me my total. Now, a couple things to keep in mind. If you don't have bounds, because oftentimes you have to start and stop at some place, you have to find the bounds. And the way you do it is set the curves equal and solve. And another thing that could happen is that the curves might cross. So, in other words, maybe you have something like this, and you say, okay, I'm trying to find this area here. Well, the problem is the curves switch behavior. So you can't have top minus bottom consistently from left to right. So what you have to do is say, okay, I'll split it into a first part plus a second part. And then I can find my area. So as an example, find the area under the curve y equals x times cosine of x squared from x equals 0 to x equals a, where a greater than 0 is the first time the curve crosses the x-axis. So notice what's going to happen with this curve is we're going to start at 0, because if you plug in 0, you get 0. Then I'm initially positive, but cosine switches sign, so eventually it's going to go back. It's going to cross. So I'm interested in this area here. So the question is, when do I cross? So we look and say, all right, we need x cosine of x squared to equal 0. Well, in order for that to be true, I would have to have that either x is 0 or cosine of x squared is 0. But I don't want my x to be 0 because I want to end up somewhere positive. So that says I need cosine of x squared to be 0. All right. So now we start thinking, when does cosine equal 0? Well, the first time that cosine equals 0 is at pi halves. So that says we need our input x squared to be pi halves. So x has to be the square root of pi halves. So our area is going to be the integral from 0 to the square root of pi halves times our height. Now our height is from our curve down to the axis. So it's x cosine of x squared subtract 0. So that's our height. Oftentimes we suppress the subtract 0, but it's still there, even if we don't write it. dx. Get into the habit of always writing down your dx's. That's important notation. And it becomes really important when you hit calculus 3, which, you know, it's not that far away, where you can do it. we'll make it. Now, how do you actually do this integral? Well, x cosine x squared is not on our list of integrals. But we look at it and we say, okay, our big tool is substitution. And there's a good candidate here. See, there's an x squared that's inside our cosine. So that's suggesting, let's make a substitution. So whenever you have a function on the inside, make a substitution. So we'll make a substitution. U equals x squared. So what would du be? Well, 2x dx. Good news is there is an x dx, but there's not a 2. Well, we'll just use our fancy erase the 2 and move it over as a half. Or if you like, divide by 2. You're allowed to manipulate the expressions to help you get what you want. So what does this become? Well, integral. Then here, the x dx is our 1/2 du. Cosine of x squared becomes cosine of u. Now, also remember the bounds. The bounds have to be changed. And the nice thing about definite integrals is you always move forward, you never move back. So our bounds were x bounds. We went from x equals 0 to x equals square root of pi over 2. We want to switch to u bounds. U equals something to u equals something. And the way we do it is we plug in our expressions, right? So x equals 0, well, u equals 0 squared. So that says our lower bound is still 0. X equals square root of pi over 2, u equals square root of pi over 2 squared becomes pi over 2. All right, so that's actually a nice bound, 0 to pi over 2. The integral of cosine is sine, so 1/2 sine of u. Evaluate that from 0 to pi over 2. Sine of pi over 2 is 1, times a half is a half. Sine of 0 is 0. So the half is still 0, so our final answer is 1/2. And there we go. And that actually is our final answer. Well, unless of course there's the final exam. I guess those will have final answers. But I do want to take a few moments and just talk about a little bit. We've had a long semester. We've gone through a lot of sessions together, and it's good to look back. So if you go back all the way to the beginning, a long time ago, we said, look, one of our goals was we want to be more comfortable doing math. And how did we get there? And I hope we did. Well, we looked at lots of beautiful ideas and lots of ways of why things work. We don't just want to take things on faith. We want to know, why do things work? And we challenged ourselves. We had lots of problems. They were new problems. They were interesting problems. And they weren't trivial. We wanted to make sure we can do problems that aren't trivial because we really wanted to learn to think. And it's hard to learn to think because that's not our natural inclination. And how do we get there? Well, we have to push ourselves out of our comfort zone. And I hope that we've succeeded in that you're able to think a little bit more. Some people may have come to the conclusion, I think I may not be pursuing this calculus any farther. That's okay. That's all right. At least you were able to have a good idea. And so I want to take this last chance to say thank you. Thank you for working so hard in this class. Thank you for keep coming back session after session. Thank you for coming to our help hours. Thank you for studying hard for each exam. Thank you for never giving up. And thank you for caring so much about this class. If it didn't mean a lot to you, it wouldn't hurt so much when you saw those exam scores. Or you wouldn't be so excited when you saw how well you did, perhaps. And I'm grateful that you took the time to be a part of this class. And I hope that in your future, you'll have many, many successes and really be able to put some of these ideas to use. I do know that a lot of what you learn in this class, you might not remember in a few years, or maybe even in a few days. But I do hope that the ability to think about new things, to learn about things, that's something you'll keep with for the rest of your life. So thank you, and good luck. Bye.